Hello, everyone, and welcome to this seminar, CSIM seminar. We have Melike Erol, okay, that she will give the seminar today. Melike, can you share your screen? Hi, Melike, we see you.
Myself.
Okay, good. Now I see.
Now you allowed me to unmute. Okay, very well. That option was locked for me. I think you are the host. That's the reason.
Oh, okay, good.
Very well. So how are you?
All good. How are you? How is everything?
I'm very good. Thank you very much. As you can see,
yes.
I am
so
down.
Yes, we see the background, but okay, good. Now we see that you're
now
sharing.
you should see my screen as well.
Perfect. So that's very good. So we can wait. Well, it is 9:31. We can wait one more minute if you want. What do you think?
Yeah, absolutely. I still hear some people are joining in.
Yeah, this is one. I see a lot of people joining, so we can wait a couple of minutes.
Yeah, absolutely. Let me just get the hang of this WebEx because I don't use it too much. During the call, how do I turn off my camera? Anyways, I can't. Oh, yes, here they are. Here are the controls. So until we start, I'm going to turn off my camera. And then while I'm speaking, I'm going to turn it back on. Okay.
Okay, perfect. And is it okay for you if we record the presentation and then we share it?
Sure, absolutely. You can record.
Okay, that's very good. Thank you very much.
Thank you.
Professor Erol Kantarci, do you think that we can start?
Yes, absolutely, Nizar. If you want to start with the introductions, I will leave it to you, and then I can start my presentation.
Perfect. Sounds very good. So welcome all again to our CSIM seminar. We are very happy and proud to have Professor Melike Erol Kantarci as our guest speaker for today. I will give some introduction. Even she is very well known now in the community. She is Canada Research Chair in AI-enabled next generation wireless network, which will be actually the title for, or very close to the title today, okay, which are AI-enabled wireless networks, okay, a bridge from 5G to 6G. And we have the expert for that. Melike is the founding director of the Network System and Communication Research Lab. It's called the NetCore Lab at the University of Ottawa, where she also is an associate professor. Okay. She has published over 150 peer-reviewed publications with more than 5,500 citations, more than 50 keynotes and tutorials and panels across several conferences and workshops. Actually, she is an IEEE ComSoc Distinguished Lecturer, beside being Senior Editor for IEEE and ACM. And she received several awards, okay, both from technical committees and from conferences as Best Paper Awards. So again, okay, the title, okay, as you can all see, is AI-enabled wireless networks, a bridge from 5G to 6G. If you have questions during the presentation, please, you can write them on the chat. Then we will ask Professor Erol Kantarci at the end of her presentation. So Melike, again, thank you very much for accepting the invitation. It is our pleasure that that you're here, and the floor is yours.
Thank you very much, Nizar. Thanks for this kind invitation and opportunity to speak to all our distinguished guests and members of the technical committee. My name is Erol Kantarci. I'm a Canada Research Chair in AI-enabled next generation wireless networks. And as Nizar said, today's talk is closely related with this topic. I'm going to talk about first some AI-related topics, of course, a couple of machine learning algorithms that are useful to us. It's very comprehensive to give a full background on AI or machine learning in just one talk. So we're going to focus on a couple of aspects, a couple of important algorithms, and then we will talk about 5G and 6G. So 5G is in the development or deployment phase already, but many of you would know research about 6G is flourishing. Nowadays, all of us who are in wireless communications are looking into what's going to be the next frontier in the next generation. So in my lab, Network Systems and Communications Research Lab, with my students, we look into the techniques from machine learning and try to apply them and tailor them to wireless communications. And we look at, of course, I mean, just to give a broad idea of classification of machine learning techniques, we have well-known supervised learning, unsupervised learning techniques, and reinforcement and deep reinforcement learning techniques. So in this talk, we're going to focus on the last one. And the reason for that is because, excuse me, there is an interactive portion of human intelligence that takes my attention particularly. But of course, as a researcher or a research group, we are not alone in this. There are many researchers who are looking into this exciting area, which are called interactive learning or reinforcement learning techniques. And the reason that is interesting is because and it's very representative of human learning. As a baby, we are not born with a handbook of the world. I mean, we don't know all the rules, and nobody tells us, like nobody supervises us about all the rules. Of course, we have our parents to teach us a couple of things, but they can't teach us everything. So we experiment with the world. And this can be considered as similar to trial and error. And if you maybe have, some background or have read some psychological tests that were done by Pavlov over the animals by treating animals to reinforce a certain attitude, you would understand that easily that if we get a reward, humans and animals actually, we tend to behave towards, or we tend to adopt that behavior rather than a behavior that is being punished. So that will give us the importance of rewarding mechanism in reinforcement learning. But first of all, I want to talk briefly about the history of reinforcement learning. And I'm not going to take it a few centuries back and start from Pavlov, although that could be possible. We can find the roots of these cognitive studies in psychology. I'm going to start it from an engineering perspective, and I'm going to go back to 1950s, and I'm going to start it with Richard Bellman. So Richard Bellman was working on optimal control theory problems, and he discovered that Markov decision processes could be a good model to model such behavior. So optimal control theory problems could be modeled by Markov decision theory, which is actually foundations of reinforcement learning. Now, in 1952, we have an interesting figure, our very own Claude Shannon from information theory. Of course, it would be a very big stretch to consider him as one of the fathers of reinforcement learning, but I included him because at the time, he also made some experiments with mice and relays in a cage, basically leading the mice or mouse, one mouse, outside the cage by the help of relays. So he did those experiments, but as I said, this is not, this wasn't one of the fundamental studies contributed to reinforcement learning, but as you can tell, there was a big interest at that time towards this area. An important study from the machine learning literature came in 1960s with Marvin Minsky. Marvin Minsky was studying the credit assignment problem, and this comes back to the rewarding mechanisms that I was talking about when I said, reinforcement learning or, reinforcing an attitude, a behavior in animals or humans. So how do you reward? If there are multiple agents, how do you split the reward? Those kind of problems are actually quite important in reinforcement learning, still understudied. And in 1970s, Harry Clough argued about one thing. And the reason he argued about it, first of all, let me give you the overall picture around those times in AI world. So it was the popular time for expert systems, and expert systems have the idea that if you give the cookbook of or the recipe book of everything around us, then a machine could be as intelligent as a human. And Harry Clough said that, or argued that, this was missing the adaptive behavior in humans. Like you can't really give all the rules around the world, and you can't teach everything to a machine like that. And in 1980s, this inspired Andrew Barto and Richard Sutton. As some of you may know, they are the famous authors of the reinforcement, or they are the authors of the famous book, Reinforcement Learning, which almost everyone who works in this area, I'm sure, have read it, or at least have read a couple of, chapters or papers from Andrew Barto and Richard Sutton. So they were inspired by Harry Clough's idea, and they developed the foundations of model-based reinforcement learning. So model-based reinforcement learning has been applied to a lot of fields, but we had to wait until a couple of more years, 1989, for Chris Watkins to come up with temporal difference equations to be able to model model-free environments or work in model-free environments. Model-free environments are particularly important for wireless people because it's very, very hard to model the wireless environment. And this also proved to be very useful for game-playing machines as well. After this, in 1990s, there was a blast of game-playing machines. Like in this picture, you see Gerald Tessura's and his, Gerald Tessura was from IBM, and his backgammon playing machine. So backgammon machines, Go playing machines, chess playing machines, they were and they are still very popular. And they helped a lot the advancements of this area. And although many of you may think using machine learning in networks is a very brand new area, actually in the beginning of 2000s, there are some studies who applied reinforcement learning to networks, wired networks, to the internet. To the applications in wireless is more recent, but still we can find some examples from mid-2000s or late 2000s. However, at the time, those algorithms were not that advanced, plus deep reinforcement learning was not in the picture. So people worked on reinforcement learning, Q-learning, and they discovered some problems, which I will talk about in a few slides later. And they said, these techniques are not super applicable. But today, with the help of deep reinforcement learning, or deep learning is helping reinforcement learning, we can have great success in these algorithms. So let's start talking about what reinforcement learning is. So in a reinforcement learning model, we have, well, let me just make this a pointer. Yeah, we have an agent. Agent interacts with an environment through taking an action. After taking an action, the state of the agent changes and the agent receives a reward. This reward is very crucial because it's going to teach the agent whether that's a good action or a bad action. Actually, this could be like reward/punishment here. So giving a punishment to the agent is possible to reinforce an attitude or behavior that's totally undesired. And if this is a complex environment, like imagine you're teaching an agent to play chess, there could be many possibilities. I mean, imagine you're moving one pawn, whether you move that pawn or the other one, the entire game, the flow of the game would change accordingly. So all of these branches that you see here corresponds to one policy, and they could have multiple extensions. But there is one bolded one, and this is the optimal policy. Now, the question is, how do we know that a policy is optimal, right? So to be able to calculate it numerically, you have to give a numeric value to the reward. So the roots of this, or the mathematical formulation behind reinforcement learning, comes from Markov decision processes. I'm going to talk about these, so let me start by making some introductions to the terms that I'm going to use without being too much boring. ST is the state of action. AT is the action that the agent takes at time t. And reward is calculated by like this. So the agent is in state ST. It takes action AT, and the clock ticks. After this, the agent receives the reward T plus 1, and it moves into state ST plus 1. So this is the next reward that the agent will receive from the system. Now, these definitions could be enough for a reinforcement learning problem when we know the model of the environment, plus the environment is deterministic. If the environment is stochastic, then we need a couple of more definitions. We need the next state probability definition, because each time that you are in state ST and you take an action AT, with some probability, you're going to land on a state ST plus 1. So that's why this environment states has to be defined by some probability. And then we can have a system where the reward is probabilistic too, like in a casino, right? You play the same thing, but you don't always get the same reward. So what happens is, if you are in state ST, you take action AT, with some probability you get a reward. So the important thing about reinforcement learning is that it's not a one-time thing. So you have to keep doing this trial and errors. And it's the fundamental difference between the psychological tests that were done centuries ago. So it's not exactly trial and error. We have reinforcement learning to tell us that this is a kind of a repeated game and the agent learns over repeated interactions. So all of these probabilities are calculated actually after maybe hundreds or thousands episodes of the same game. Like if you're playing chess, you play it multiple times. And then the policy is the behavior of the agent from the start of an episode to the end of an episode. And it's the mapping from states to actions. So if you put those words into notations, what happens is we have the policy pi as a mapping from states to actions. Every policy has a value, has a numeric value. And that numeric value comes from the numeric value of the reward. So the cumulative expectation of the cumulative rewards gives us the value of a policy. Now, for an infinite horizon problem, we don't have to have this discount factor. We can just look at the summation of the rewards. But usually we want to generalize the problem. So we look at infinite horizon. At the infinite horizon, we're going to add all the rewards from now till maybe hundreds, thousands of steps later. But imagine you're giving the same weight, same importance to an event that's going to happen 1,000 steps later. Does it make sense? Most likely it doesn't. I mean, most of the problems that we work with, it doesn't make sense. So what we do is we use a discount factor, gamma, to discount the value of the reward at the future steps. So that's why as this index grows, the discount value degrades its significance, importance. So in the closed form, we can write it like this one. Now, here comes Bellman, Richard Bellman's equation. Richard Bellman formulated the optimal policy as the action that maximizes this equation. And this is actually the iterative form of this equation, only adding that the probability of the environment, so the state transition probability of the environment. If you have a deterministic system, you can actually cross this out. But most of the systems are stochastic, so we would like to put it to. And this V star ST of ST can be calculated as you can notice here as V star of ST plus 1. So if we know the probability, the state transition probability of the environment, we can use dynamic programming to solve this equation. And for model-based environments, this is actually what it has done. However, in wireless and in networks, we are usually faced with lack of models. I mean, we have some models, but if they were good enough, we wouldn't be using reinforcement learning. So to free ourselves of a model-based environment, what most researchers and we have been doing is using Q-learning. So Q-learning relies on temporal difference equation that was put forward by Chris Watkins. And in this one, what happens is that the Q values are taken from a table. Okay, so note it down. This will be important. They have to be stored in a table. And they're compared with the next value. So if they are improving the reward, the value of the policy, the Q values, then the next actions are selected accordingly. Now, you see gamma over here, we have the discount factor factored into the equation. And then we also have an alpha. This alpha is the learning rate. If you have a large alpha, then your learning rate, the steps become larger, so you may miss some important steps in between. If you have a small alpha, then you may go with very small steps and your convergence time might be longer. So those parameters are usually need to be tuned in Q-learning problems. Another important mechanism before we go into other details is the exploration phase of Q-learning. Now, as you might have noticed, the nature of Q-learning is quite experimental. Like you try some Q values, they don't look good, then you change to another one. So there has to be a mechanism to save us from being stuck at the local minima or local maxima points. to get us closer to the optimal solution. So we use Epsilon greedy approach, or Epsilon greedy approach has been proposed in the literature and has become very popular to deal with this problem. Epsilon greedy approach is something like this. So with some small probability, you take a risk and you do a risky action, which maybe in the end, a couple of steps later, will give you better rewards. But with a large probability, you go with the safe actions. So 1 minus epsilon probability, you go with the safe actions. And there's an interesting story about that. Google researchers, when they designed AlphaGo, the Go playing machine, and the machine was playing against a human, what happened is during a match, the machine took a risky action. And all the designers, programmers thought that it was a mistake. So the machine was going to entirely, lose the game. But then they noticed that the machine was doing this exploration strategy. It took a risky action to explore better rewards. And in the end, the machine actually won the match. So it is a useful technique. It is almost a must that you have in Q-learning. Now, I'm going to come back to the point where I said in Q-learning, we have a table to store the Q values. Now, you might have noticed at this time, or at that time when I said it, or if you haven't noticed now, I'm going to pull your attention to it, that this might be problematic, right? Because you have to store, if you have a problem with the large state and action space, then that's a huge table that you need to store. And if you have a continuous state space, then that's a problem too. So in most problems, what we do is, or what we would like to do is, we would like to have a function approximator. So what's a function approximator and how are we going to use it? So instead of storing the entire big table, you fit a line, let's say, to the values. And, from anybody who knows a little bit about estimation, the first technique that we would think is regression, right? And if you do linear regression, that's the simple one. So you have some values and then you just draw a line. Now, drawing a simple line, a linear line with 2 parameters would be very primitive, and we would not be able to model the Q values that we have very accurately, obviously. However, if you were to parameterize this model and use multiple parameters, the more you use, you approach to the real data. But of course, there's always a trade-off how much of parameters you need to use to model a data, right? You can use as much as the data, but then it doesn't become a model anymore. So you can apply some filters for that. And a nice definition of, or a combination of filters is neural networks. So that's where deep reinforcement learning comes into the picture. Before I talk about the deep reinforcement learning particularly, I want to talk about the neural networks and then bring the deep part into it. And some history lecturing again. So the father of neural networks, let's say, are the perceptrons. Perceptron notion was developed in 50s, 60s, again, the same timeline where AI was a really very hot topic, by Frank Rosenblatt. So he came about this idea. If we were to have a decision circuit and the inputs x1, x2, x3 were inputs to a circuit with certain weights, and we had a decision over here, like a simple decision that you see here, that the weighted sum of the inputs are compared with the threshold. If this is less than the threshold, we get 0. If this is more than the threshold, we get 1. Very simple decision circuit. Then, we could at least have a way of determining the impact of these inputs. And maybe this could help us with some classification of the inputs. Now, the learning process would be what? The learning process would be learning the weights. And as a simple perceptron, it's very limited capability. But as we change this function to just from threshold checking to things like sigmoids, so making them activation functions, and putting those neurons into the same layer or sometimes in multiple layers gives us the capability of modeling much complex problems. But the problem of estimating the weights is the same thing. So the the learning happens by estimating those W's that we see over here. Now, if we have one input, one output layer, that's a shallow neural network. If you have multiple hidden layers in between, that's a deep neural network. The beauty of deep neural networks is that they can represent the data in a much compact way. Actually, according to the universal approximation theory, we could have modeled any function by just a single, straight set of neurons, but the number of neurons would have to be really a lot. So people in machine learning literature have come up with compact architectures. Some of you may heard CNNs, convolutional neural networks, or maybe you are familiar with recurrent neural networks as well. So these are all compact, multiple layer neural network architectures, and they are useful for different purposes. CNNs have been very popular for computer vision, image processing, whereas RNN have been very popular in NLP. Actually, let me go back to the history one more time and talk about the times when AI winter came around. So for a while, during the Cold World War, AI and natural language processing specifically was very hot. So there was a lot of funding from DARPA because, US wanted to decrypt text from Russia, but funny translations came out of the translators at that time. I mean, the machine translators. So there was a belief that machine learning was not doing the success that they wanted. So there were funding cuts. And some researchers even left the field. They started working at different areas, but then there were some others who insisted working, luckily, and they kept developing the area. So at the beginning of 2000s, this recurrent neural network idea came up, and actually it was a breakthrough in natural language processing. The reason I'm talking about this too much is because it's important for networks as well. The beauty of recurrent neural networks is that they can catch the historic information. So if there is a temporal sequence and you want to go back like 1,000 steps, 100 steps, and remember what happened, what decisions you took at that time, recurrent neural networks can be helpful to you. So this is a very simple architecture like the chain that you make, but we have a special recurrent neural network as long short-term memory, or LSTM, as a lot of people I'm sure have some familiarity with. So Lstm is actually something we use a lot in our studies, and a lot of people in this field are using. The beauty of Lstm comes from that it has two inputs. So one of them is the memory of the previous unit. So you can carry memory with you to the next units. And then, as usual, we have the output of the previous Lstm unit. There are certain gates, for get gates and input gates, that help us filter or shape the information that we receive from the previous layers. And then again, at the output, we have the output to the next unit and the memory to the next unit as well. So let's just try to, gather our thoughts about what we have been talking about. So we talked about reinforcement learning as an interactive learning technique. And then I said we have Q-learning to model the model-free environments or work on the model-free environments. However, I said Q-learning can end up having very large tables, so we want a function approximator. Then I started talking about neural networks. Now, how are we going to tie all of these? Actually, in 2015, there was an article in Nature written by Google Mind researchers, and this is like where deep reinforcement learning, the way that we use in today's problems, have been described. So the idea of having a function approximator for Q values stay, but a couple of important things have been proposed in this article, and they help with the stability of deep reinforcement learning. So it's not as simple as you put a function approximator tied to the reinforcement learning unit, but we also have a deep neural network and a target deep neural network where we copy the training sample. So we keep a copy of the previous version of the trained neural network. And then we have an experience replay memory to get the mini batch of examples, trained samples, to drive the next states and rewards of our Q-learning problems. So this way, this form of deep reinforcement learning has been applied to many wireless problems. And as you can see in this picture, we have the G node B. So you can see like this was something that has been applied to a wireless network. And then here we have the environment as the channel itself, the wireless network itself. And I'm showing here a feedback, and the natural feedback from the environment would be the CQI values that we can obtain from LTE or 5G networks. Of course, you can have many different feedbacks, you can have many different designs, but this is showing one design with deep reinforcement learning as referring to the architecture that was proposed in the Nature article in 2015. Now, so this is all I want to cover about the AI or machine learning part. Now, in the title of my talk, I have like AI as a bridge from 5G to 6G. So at this point, I want to, switch gears a little bit and talk about the wireless aspects and how AI will play a role in the switch between, or the being a bridge between 5G and 6G. So this picture was drawn by ITU, International Telecommunications Union. And since the time it was drawn, actually the ideas about 5G changed a lot. It is sort of an old picture. I mean, old in our language is quite relative. In some disciplines, old is like 100 years old. In wireless communications, old is like a couple of years back. But still, I'm going to talk about it, and I'm going to talk why we think about it differently these days. But we still use the use case definitions as defined here. For example, we have the enhanced mobile broadband for users, humans like us, uploading, downloading videos, sometimes, playing XR, VR games and stuff like that. We have the ultra reliable and low latency communications, could be a technology for self-driving cars, mission critical applications, or industrial automation, industrial IoT, and smart factories. And then we have massive machine type communications, where in the smart cities, a lot of gadgets needs to be, or smart cities or smart homes, a lot of gadgets needs to be connected. One funny or nice thing about this figure that I usually like to point out is like the voice communications. This is where the first generation of mobile communications started. We were just, we wanted to have the ability of calling someone where we were outside of our homes, maybe sitting at the backyard or in a car or something like that. But look where we came now with the 5G. It's no longer about only humans. It's about machines talking. It's about cars talking, or people doing all sorts of video intensive applications, or even sometimes going to tactile or other transmission of other senses. Now, the reason I said, we diverted a little bit different than this picture is because actually for this one, ultra reliable and low latency communications. So in today, when we look at this, it's very hard to group these two requirements together. So if we were to draw this picture today, we would draw it like a rectangle, putting ultra reliability in one corner and then low latency in one corner. Although it might be desirable to have them both, having them together is very challenging. So it's still a problem in 5G, we can say that. Now, all of these technologies were like the use cases that would drive or be the killer applications of 5G. Now, from one generation to the other, except then, killer applications, you also need some new technologies. And millimeter wave was one of the driving forces behind 5G. Millimeter wave plus numerologies, plus flexible architectures, virtualization, and all that came into the combination, mix and make 5G. Now, these days, we are eyeing 6G. What will be the definition of 6G? What's going to be the technologies that is going to be included in 6G? It's almost like fortune telling, because, there's 10 years almost from now, or maybe 9, since we see another rollout of a next generation of a mobile network. However, the standards are being formed these days. So it's not, even if we don't see the deployments, the research is, going on in this directions. And, a couple of years down the road, the standards, the releases written by 3GPP would be referring to the 6G architecture. So we're not that far away from what's going to happen in a couple of years in the mobile world. So they're all these different technologies, starting from terahertz, maybe NOMA to be included, the use of unlicensed spectrum or cognitive use of spectrum, aerial networks, drones, visible light communications, and another active area, intelligent meta surfaces. Those are all, quite active research areas. But one thing that industry, and this is something I've seen in the last maybe 2 years or so, in every keynote that you go in a big conference, it's almost impossible to miss a slide on AI. AI is the next big thing in wireless communications. And when we say AI, we talk about network automation. And it is a big aspect. I mean, operators, when they talk about AI, they just talk about taking automated decisions when a failure happens. Like right now, there's a human making those decisions, so removing that human. For researchers, when we say AI, we look at it maybe at a bit futuristic perspective, and we say, completely making it closed loop, no human intervention, all the parameters, sub-parameters tuned by the machines, and then all the failures, all the problems are also troubleshoot by the machines. So we are not there yet, but there is quite a significant amount of research in this. And one may ask, why now? What has changed so much? So there are two things that has changed. Number one is growing complexity, and number two is availability of data. First, let's talk about this growing complexity. So from 4G to 5G and from 5G to 6G, what we are seeing is more and more small and directional cells. And this is because of the underlying physical layer technology. So with millimeter wave, the propagation distances of the signal is, by physics, it's very limited. So what you need to do is you need to beamform your power into a certain direction. So that creates directionality. Even when you do beamforming, your signals cannot travel further, like kilometers away. So what you do is you use small cells. Small cells means dense deployments. You put a lot of base stations to cover a certain area. Then that brings the problem of what? To intelligently configuring all these base stations and optimizing their performance. So complexity brings the need for smart algorithms. The next thing is massive number of devices. With IoT, we're going to have lots of devices that's going to be connected. Of course, don't get this wrong. IoT devices use different communication techniques as well, but 5G is just seeking some market opportunity there. And if that comes into the picture, then we should have the technologies ready for that. And then massive MIMO, massive number of antenna arrays. Here and there, I'm sure you're hearing some news from vendors saying that, oh, we did, 128 MIMO, we did 265 MIMO. So each day and day, their antenna technologies are getting better. And, this is increasing, this is something increasing complexity as well. And then the mobile integration of multi-access edge computing. So previously, when we look at a cellular network, it would be just the cellular network. So you make a call and then, the network allows you to speak to someone. But these days, the networks are also helping with computations to especially computational limited devices. For example, you have a phone, your battery is about to die, and you are doing for some reason, some computer vision job. So you are able to offload this task to a multi-access edge computing. Plus, the computing infrastructure with the virtualization of RAN is becoming a part of the RAN as well. So some of the network functions are running on virtual machines. In the core, this is already done. This is the practice. But for RAN, radio access network, this is becoming a reality. And there is the aspect of ORAN, which is opening up the interfaces, bringing up a multi-vendor environment, again, increasing complexities. And let alone network slicing is also bringing a lot of complexities that requires automation and no human in the loop kind of operation. This is what we call actually closed loop. So that's why we say AI is the next big thing in network automation. And it's going to be the big thing in 6G. And that's the vision that we believe in AI-enabled wireless networks. So let me just check my time. After this point, actually, I'm going to talk about a little bit of some example work. So I'll try to help you better visualize those techniques that we talked about: reinforcement learning, deep reinforcement learning. We talked about 5G, 6G, but come on, how do you apply to a real problem, right? So I'm going to talk about these in the next few slides. So in our article in 2019, that was published in IEEE Recurrent Technology magazine, we proposed, or we suggested, some of the places where AI or machine learning algorithms, more specifically, could be applied. And we focused in this article to reinforcement learning and deep reinforcement learning. So I'm going to start by a very well-known example of resource block allocation, and I'm going to show Q-learning application to this problem. This work was something that we proposed and presented in IEEE GlobeCom, and this was the last conference that actually I went to. And you know, if you look at my background, you can tell that I have really missed traveling, especially to exotic places. But due to COVID, we cannot do this at this time, but we can always imagine ourselves to be in different places. So in this work, we looked at 5G new radio, its numerologies, and its flexibility in the numerologies. So every TTI, first let me introduce you the essence of the resource block allocation problem. Every TTI, the base station, needs to make a decision to allocate its resources to its users. This is true for uplink and downlink. The resources, what are the resources, right? Let's demystify this word. The name of resources comes from OFDM. OFDM splits the channel, the frequency, into subcarriers, and the information data is transmitted in parallel in the subcarriers that are assigned to this user. There's also a time split. So as you can see on the vertical axis, we have the split of the frequencies, and on the horizontal axis, we have the split in the time. So once you get a bunch of subcarriers, you don't use it for your entire lifetime of a communication. You hop from one time frame to the other, and you can grab a chance to allocate maybe 6 consecutive time frames, but then you will have to wait for the others, or you may change to another group of subcarriers. So small block of, or an element, resource block element, is defined by OFDM symbol time in the time domain, and the bunch of subcarriers that you are assigned to in the frequency domain. So the Downlink Scheduler would allocate these resources to the users who are downloading video, for example. And in this paper, we assumed 2 types of users. So eMBB users would be the ones who are downloading video, and they care about their throughput. We have the uRLLC users, ultra reliable low latency communication users, who would like to have low latency and reliability. So these are all conflicting demands. So we would like to have an intelligent scheduling algorithm at the base station that's going to help us schedule these users in the best possible way. And as I said at the beginning, Q-learning can become very space intensive if we use a lot of states and if we use a lot of actions. So for that reason, in this problem, we try to minimize or use as less as possible modeling parameters. We use the state as, or we define the state as a desired state and an undesired state, where the desired state is related with the SANR. When the SANR is about a certain threshold SANR, we say we are in the desired state. And the action is choosing that resource block element or resource block group in the big grid picture that I showed in the previous slide. So to reinforce our agent, the design of reward is very important. We want to have a proper reward that's going to drive our agent to the intended action. So let's remember what we are trying to do here. We are trying to improve the throughput for the eMBB users, and we are trying to improve the latency of the uRLLC users. So the throughput is related with SANR. Signal to interference noise ratio. So if it's above a certain threshold, then we check the latency. We want the latency as close as possible to 1 millisecond. So we give partial rewards, 1 minus maximum waiting time in the queue, to the latency. So this will give the partial reward to the agents. And if the SINR is not good, the agent is punished. So there's a reward and a punishment phase in this model. And with this, we were able to show that, so we looked at under two different load regimes, low load regime and high load regime. And we compared our algorithms with a priority proportional fair algorithm that was proposed and studied in a study that was almost proposed a couple of months ago from ours. And over there, the reliability was maintained by setting the HIRQ values to just 2. And that's why I said previously it's challenging to have both reliability and ultra low latency. If you reduce the number of HIRQs, you can have less latency because you are retransmitting less, but then you will be sort of compromising your reliability. Anyhow, we were able to, those are all side discussions, we were able to show that our proposed scheme was performing or having better latency for uRLLC users. And it didn't come at the expense of jeopardizing the throughput or eMBB users, because that's really important. I mean, you can do one thing good for one particular user group, but if you're, doing really harming the performance of the others, that's not a good performance enhancing scheme. So we demonstrated that we can have better throughput for eMBB users, and the overall packet drop rates for all user classes were better than the priority-based proportional fair algorithm. Now I'm going to switch gears a little bit because, that was something we did using Q-learning, and we looked at resource block allocation, but resource blocks are not the only resources in the wireless world. There's also the power resource that we would like to schedule properly or assign properly to the users such that they don't create that much of an interference. So in our, a little bit more recent than the previous work that was published in IEEE ICC conference, what we proposed was something suitable for a millimeter wave and by using NOMA. So as you might know, NOMA gives us the opportunity to schedule users in the same resource blocks, but they should have different or varying power levels. The way, the trick about NOMA is that the receivers will decode these signals. They would do successive interference cancellation. Successive interference cancellation would work only the interference between interbeams are handled properly. So in this problem, we focused on two things. First of all, user cell association, and then beam power allocation. So imagine you have two users right in the intersection of two beams, two cells. Which user will connect to which cell or which beam? And after that, what will be the power allocation for these beams? So we tackle this problem jointly. For that reason, we have a joint action space. So there are two variables in the action. In the previous problem, it was only one. We were doing the resource block allocation. Here we are doing the power and user cell association together. But we wanted to keep our state simple because this is still a Q-learning based solution. We don't want to explode our states and action space. So if the average SINR is above a certain threshold, we say we are in the desired state, and the reward is a simple one here because we are considering about the throughput intensive users. So if it is, if the SINR is above a certain threshold, it's a desired reward. It's the desired behavior. We want to reinforce it. The reward is 1. And in the other cases, the punishment is -1. Now, I'm going to look at the plot in the right-hand side first, because that shows us the KPI. The left-hand side, I will come back in a minute. So we were able to show that our Q-learning-based solution is better than, is performing better than a uniform power allocation scheme in terms of some throughput. And at the side, it had better latency and packet drop rate results. But another thing that we are seeing in this slide is actually the convergence, which I didn't show for the previous one, but in the paper we also had it. The reason I want to have this discussion is because it's an important thing in reinforcement learning. And one might imagine, like, because in the very beginning, I said this is like a trial and error. You do multiple trials, you learn. And one, fundamental question that people would have in their minds is that, if we're going to do like so many trials and errors, how are we going to do it in a real base station? Like, are we going to let the base station, do some nonsense allocations and then, degrade the performance of some users and then in the end learn what's going to happen? Eventually, if you put reinforcement learning out of the blue into the system, that's what's going to happen. But mostly we envision is that there's an offline training phase. So the base stations, the algorithms are trained offline under certain, stationary cases from one to the other. And then they learn particular working regimes and their converged versions would be put on the field to work. However, even though it could be online, I mean, the reinforcement learning or deep reinforcement learning can be trained offline, this training time is still very important. And as we have shown in this paper, the training time can be as long as 2,500 TTIs. This is a long time. So in our next studies, we focused on how to reduce this training time. So I think, I'm running a little bit out of time. So I'm going to skip this work and I'm going to just talk about the convergence issue because that's an important one. So this was describing our GlobeCom 2020 paper where we used two learning techniques, one unsupervised learning DB scan and for clustering the mobile users into a beam and then using deep reinforcement learning for resource block allocations within a beam. But let me go to this more recent and interesting work that I would like to talk about, which has its roots in a concept that's called transfer learning, and that has been known in machine learning literature for a while, but mostly for supervised learning systems. So in supervised learning, people have thought, we're working on a classification problem, but why are we teaching the agent over and over the same things? Wouldn't it be nice if the agent would extract some information from how it classified the samples previously and apply it to a new classification job? So around 2007, there was this article about transfer learning via inter-task mappings for temporal difference learning. So this actually has been an inspiration for our recent work on transfer reinforcement learning in 5G millimeter wave networks. And right now, actually, there are a couple of emerging papers in this area, but to the best of our knowledge, we were the first ones to propose transfer reinforcement learning to help base stations first of all, map some functions in between expert G-node bees, which can stay offline and learn particular actions, and then transfer this to the learner G-node bees who are working in the field. So in this problem definition, what we did is we assumed we have expert G-node bees that are gathering some general knowledge. This is general because their model, their environment model, is first of all an omnidirectional model. So there is no beam forming. So we are learning just user cell association, and expert G-node bees are using an intelligent algorithm, more specifically Q-learning. So after they learn this, we have a mapping function between the learner G-node bees, but learner G-node bees tasks are a bit more complicated. They're going to decide the joint user cell association and the selection of the number of beams. And for this one, we are using transfer Q-learning. So I'm not going to get into the details of the G-node bees and learner G-node bees models, but as you can see here, we have the capacity definitions over here with SNR values defined with channel indexes. And then because this is an omnidirectional model, we don't have that much detail, but in the millimeter wave model with the beam forming, we have much detailed models that we borrowed from the literature, and we model these expert G-node bees and learner G-node bees accordingly. At the end of the day, of course, we looked at the KPI, and I'm going to show them later, but I want to focus on convergence. We showed that the convergence of expert G-node bee for Q-learning is happening like around after a couple of thousands of TTIs. But what's most important, because this is offline, this is still okay. What's most important is that the learning of the or the convergence of the learning of the learner G node B, who is transferring knowledge from the expert G node B, is improving. So we can both achieve higher rewards than applying simple Q learning instead of using transfer Q learning. So we have higher rewards with the dashed lines, and the convergence happens earlier than the Q learning technique. However, we still have room for improvement, and I find this area really very important area to work on. And in any networking paper, we need to look at the performance results, the KPIs, and we showed that under mobility and the stationary users, our proposed transfer Q learning scheme was better than the baselines, the Q learning one, joint user cell association using best SANR and DB scan, plus the traditional sectorized cells approaches. Ours is performing better than these ones. So I'm going to wrap up my talk in a few minutes by just making remarks about the fundamental things that I talked about. So I talked about AI winter that we saw in decrease of funding and stuff like that in machine learning literature. I think in terms of networking, we are in AI spring. So there's a lot of research interest, both from academia and industry. And as I had mentioned before, there are two reasons. Number one is systems are becoming more complex. Number two is we have more abundance of data, so we can make use of it. But still, I mean, I usually make this point in my talks because we don't want to be misleading as researchers. We don't want to paint a pink picture and say, okay, AI is the whole solution to your problems. There are still problems in machine learning techniques, and I don't think they are ready for prime time. But that doesn't mean that we shouldn't do research on it. Actually, the opposite. We should do more research on these techniques to ensure that they are ready for prime time. Convergence is one big thing that needs to be taken care of. Scalability, I mean, usually what the techniques that I showed, and a lot of people work in the literature, they're like 1 or 2 base stations, but we have to look into much larger scenarios. Then if you're using some supervised, unsupervised learning techniques, you definitely need standardized training sets, which we do not have much out there. Usually in wireless, we talk about distributed systems, distributed agents, so convergence and all these problems escalate in distributed systems. And another very important problem and challenge is learning from the rare events. So I'd like to finish my talk, I hope I'm on time, with acknowledging my students. I have 15 students in my lab, and most of these works today I presented are from my recently graduated PhD student, now a doctor, Dr. Medhat El-Sayed. But we have a lot of upcoming works with the team members, and our research is funded from generously funded by the agencies in Canada and CERC from US, NSF, and MITAC's Ontario Centers of Excellence Center Encore 5G project. With this, I would like to thank all of you for your attention, and I would be very happy to answer your questions.
Okay, thank you very much, Mel, for the really nice and insightful presentation. It is really interesting, the topic and the presentation itself. So I have some questions that if you are so kind to answer. Well, the first one, I think it is a very common question that I see in so many tutorials about whenever it is about AI, and it says that, for example, in 6G, there will be a lot of IoT devices that have low capabilities for processing and for storage and for communication. How do you think that AI and reinforcement learning would do with these devices, and what are the new updates that have been proposed to the other specific for these resource constrained devices? We would like to hear your opinion about it, please.
Excellent question, Nizar. And actually, thank you very much for asking this, because this gives me a bit of an opportunity to talk about this area as well. Because, I mean, the talk is mostly focused on resource allocation problem, but AI is applied in physical layer. AI is applied in task offloading, as you mentioned. It is applied in network slicing. So if you were to give a comprehensive talk on, you know, all these techniques, I think that should cover like 4 or 5 hours. But if we speak about task offloading for those resource constrained devices, AI can be really helpful. And we have a recent ICC workshop paper, I think it's presented just a couple of days ago, which I didn't include in these slides, where we look at partial offloading and entire offloading scheme and trying to optimize the decisions of the devices when there is capacity at the multi-access edge computing device, and also capacity of the wireless to transfer this processing tasks, that we either entirely offload the task allocations or partially do some computations. So with multi-access edge computing, with offloading problems, there is a humongous growing literature in the area, and we have some interesting studies as well. And another interesting topic that I find really dear to my heart is the integration of age of information as well. Because when we talk about those resource constrained devices and their offloading, it becomes really important. And you talk about an AI technique that may have a very long convergence time, then you need to be really careful about that your information does not become stale when you use it. If you work on an obsolete and old data and tune all your algorithms according to that, you may end up with an observation of an environment which happened in the past, but you don't want to do that. You want to use the best useful update. So there are a couple of things here. First of all, what to upload, when to upload, and then when not to upload, because sometimes, you know, that information might be already stale, or you might be using a stale information. We have a JSAC paper on this that is just accepted a month ago. So if the audience is interested, I can send the information about that as well.
Yes, I think that we will all be interested. Is it in your website, so that we can? There is a link that we can download that paper, or not yet? Or is it on archive, or well, if you can share it with us, I can.
I will do it in the chat window. I just have to get out of this full screen mode.
The chat, yeah, you will find it to the right, low bottom area.
Okay, why don't I stop sharing? And yeah, you'll be able to see me in a bigger picture. And yeah, I'm able to see my screen as well. Yeah, I'll put it in the chat. Yeah.
Okay, good. Thank you very much. Well, actually, one question also, whenever you said about offloading some of the tasks, an interesting area that has also received a lot of attention with AI is federated learning, so that we don't make the learning on one single entity or device or processor or GMB, but to be distributed over several devices. But yeah, it is well recently proposed. I saw a paper that they said that it is for 6G. What do you think about it? You, from as an expert, what do you think about federated learning? Do you think it has a future, or well,
it is a very popular area.
Yeah.
It is a very, very popular area, and this is something I've been reading a lot lately as well. We don't have research into that, so I haven't been working in that area, but there are two aspects of federated learning. Number one is that if you have a huge amount of data to learn from, you can engage distributed devices to train themselves each locally. And then share the model parameters with a parameter server, and iteratively, both the local learners and the server tries to converge to a global model. Now, two things here. You can tune the physical layer parameters quite nicely with federated learning techniques. But I see that there is more of a literature growing in the area of how to tune wireless parameters to make federated learning better. Our colleagues, Walid Saad, Mehdi Bennis, and Vincent Poor, I think they can be considered as the prominent researchers in this area, and they have mostly contributed to this area. How do we assign the resources such that federated learning performs its learning task in a most optimal way? And if there are losses in information, how the training performance is not impacted? Because I mean, federated learning, frankly, didn't born out of wireless. It was developed by Google researchers, and they were training text messages independently on the machines of users. So without, like you type a text, but Google doesn't want to get to your device and get your data about what you type. Instead, they want to get the model parameters of what you type and learn, how you're going to type in the future. So they developed federated learning. But wireless researchers discovered that because all these devices, IoT devices, will be working in a wireless domain, they also need to be resource efficient. So if you are learning something and transmitting thousands of parameters in the wireless domain, first, is there a way to compress this information? If there is, how do we do it? Then how do you allocate the resources to select the best learners among this distributed learning scenario? Then how do you do it in a training efficient time? So how do you minimize the training loss? These are like the fundamental problems in federated learning, and I find this area very interesting as well.
Thank you very much. Yes, very insightful. Well, one last short question from my side. It's about the convergence. I saw some of the results. I don't know what is your experience about because the scenario changes. So is it the convergence with respect to the coherence time of the scenario, the mobility model of the user? Sometimes it could be large, so it can jeopardize reinforcement learning. What do you think about it?
That's a true observation. For non-stationary systems, convergence can be a problem. So the way to deal with this is looking at cases where we can learn from less experiences. And offline training, I think, is the key to this problem. And we have to also remember that, I mean, we are not the only ones using reinforcement learning for real problems. Actually, self-driving cars are also using reinforcement learning and deep reinforcement learning. And, believe it or not, they are faced with much variable situations than the wireless network. So their problems are much bigger than ours. But with offline training, and training under certain circumstances, they can get success. So I think we still have to work on convergence or convergence under non-stationarity and these kind of things. But I can say that there is a light at the end of the tunnel, so we should be aiming that.
Yes, I completely agree. Well, that was the last of my question. So I don't see here more questions from audience. So, well, we come to the end. We were very happy to have you here. Very interesting presentation. Thank you all again for accepting our invitation. It was our pleasure. And thanks to all the participants who were also in the seminar today. Thank you.
My pleasure. Thank you very much, Nizar, for the invitation.
Bye-bye. And thank you all, and please stay tuned for next seminars that will be announced through our mailing list. Thank you very much for joining. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.